Hey guys, thanks for tuning in. This is Notes 14.1, 14.2, Chapter 14, Chemical Kinetics. What is kinetics? Kinetics is study at the rate at which a chemical reaction occurs, or how fast a reaction goes. Besides information about the speed which a reaction occurs, kinetics also sheds light on the reaction mechanism, and we'll talk more about that much later on. So factors that affect reaction rate. Reaction rate in reference to how fast a reaction proceeds. So one of them is physical state. Obviously you would expect something like solids. If you have a block of substance A plus substance B, okay, and they are both solids, this is not an optimum physical state for the reactants, because the reactant particles have to come in contact with each other. So unless those solids were powder form and you mix them very thoroughly, most reactions don't work with two solids. Most times we take a solid, dissolve it in water, and then we take another solid and dissolve that in water, and we combine the two. And it's the water that acts as a solvent that provides a good medium for the molecules to come in contact with each other. And when you mix that solution up real well, that's how you get the homogeneous mixture. Which helps molecules combine the fastest. Other factors that affect reaction rate. Concentration of the reactants. Of course, if you increase the concentrations, you increase the number of molecules, which also increases the likelihood that those molecules will come in contact with each other and produce products. So increased concentration increases reaction rate. I do want to say one more thing though. So the finer that you make the particles, or whatever state it's in, the best way that you can, like if you increase surface area, you increase the reaction rate because you increase the number of molecules that come in contact. That's for the physical states of reaction. Okay, so concentration increases, reaction rate increases. Temperature. If you increase the temperature 10 degrees Celsius, you typically double reaction rate. For a reaction. That's a very general understanding that increased 10 degrees Celsius doubles reaction rate. So at a higher temperature, the molecules are moving faster and have a better chance of colliding more often to produce products. Presence of a catalyst is the fourth one, and this is the one you probably see the least. Just as an example, there's two ways that you could have a catalyst. You can have a catalyst that is different from the reactants, such as a piece of platinum. Platinum is often used for organic or biochemical reactions because it provides a good site for a reactant to come in, mix with another reactant, and then they form the product and leave again. So that means platinum is a good heterogeneous catalyst because it's different from the reactants. It's a metal and not like the other reactants. Then there's other kinds of catalysts that get very involved in the reaction but end up looking the same when the reaction is done. This is hydrogen peroxide. Hydrogen peroxide breaks down to water and oxygen gas, but it does that very, very slowly unless you mix manganese dioxide. MnO2 is a compound that helps create an environment where H2O2 can decompose very quickly. So MnO2 would be a catalyst, and that's why you see it above the arrow. That's typically where we put the catalyst. As we continue on for reaction rates, the rates of a reaction can be determined by monitoring the change in the concentration. If we have a simple reaction of A turns to B, you will notice that A decreases over time and B increases over time. So if we are checking the concentration of A over time, you will see what happens to A. It decreases. Notice that the decrease from 0 seconds to 20 seconds of minus 0.46 moles for A is actually less when it goes to the next one. Notice that here, 0.46, it's decreased another 0.24 moles. It's typical for a reaction to decrease in reaction rate as the reaction continues, and we'll talk about why in 1 second. So reaction rates, here's another one. This is called, this substance right here is called butyl chloride. It's got the chloride at the end. And when we mix that with water, what we do is we get an alcohol on the other side, which is the OH at the end. This would be butanol. So butyl chloride to butanol, and notice that we produce then hydrochloric acid. So what's important here? What's important is to see that as you go from butyl chloride to butanol, mixing with water, that we have a reaction. We're only checking for the butyl chloride, and that M is for molarity. Okay, so the molarity of the butyl chloride goes from 0.1 molar all the way down to 0.02. So in this reaction, the concentration of butyl chloride was measured at various times. Notice it starts off at 50, and it goes for every 50 seconds until we hit 200, and then it goes for every 100 seconds. So the time span is not constant throughout. But notice that each time they take a measurement, it seems like the reaction is slowing down little by little. So if we take the average reaction rate is simply subtracting these two concentrations and dividing by whatever time change there is. So I would subtract these two, and then these two meaning 0.1000 and 0.0905, and that would divide by 50 seconds. And that gives me 1.9 times 10 to the negative fourth. Notice that this reaction rate, that this average rate of 1.9 times 10 to the negative fourth molarity per second decreases the further along you go. Well, what happens if we graph that? Oh, by the way, the average rate is shown right here. And the delta means change in concentration. That's what the brackets mean. Concentration, and in most cases this is molarity. Okay. And change in time. Notice that the average rate decreases. This is because the reaction goes, there are fewer reactants to mix and produce product. So that makes sense. But if we graph it, then we see a little different picture. And what they did was, when they graphed it, they took the very first point here at 0 time, and they drew a tangent line, and then figured out what the slope of the tangent line is. So you plot the concentration versus time, and this reaction yields a curve like this. The slope of the line tangent to the curve at any point is the instantaneous rate, not the average, but the instantaneous rate at that time. So the slope of this line that you see here, whatever the slope of that is the instantaneous rate at time 0. As it turns out, the best indicator of the rate of the reaction is at time 0. So the tangent line slope at time 0 is what we're looking at. Okay, in this reaction, the ratio of butyl chloride and butanol is 1:1. So that means that as we're decreasing the amount of butyl chloride, we are increasing the amount of butanol at exactly the same rate, because it's a 1:1 ratio, because there are no coefficients in front of C4H9Cl and C4H9OH. So what if it's not 1:1? What if we have a situation here where we have hydrogen iodide, but it's 2 moles for hydrogen iodide for every mole of hydrogen, every mole of iodine? Okay, so then how can we compare the rates of this disappearing, because it's a reactant, to this increasing and this increasing? So here, notice that the HI gets a minus sign because it's a reactant, because it's disappearing. And 1/2, here's how we see the coefficients. They come 1/2 to give us rates that we can compare to each other. So again, the delta and then the brackets in HI means concentration divided by delta time, the change in time. So change in concentration for I2 then divided by the change in time. Okay, in general, here's what it looks like. For any reaction that has coefficients lowercase a and capital A for the formula, and lowercase b and capital B for the formula, Then we have over here the products of lowercase c for the coefficient of c, and C is the capital C is the formula for the compound. Same with lowercase d and capital D. Notice that we got negatives for the reactants and positives for the products. Okay, take a look at that equation. What you see here for rate equals, that's an excellent quiz question. And that's it for today, guys.